Okay, October 20, exam 1. These are example problems from old exams that I gave for this part in the course. So, you need to practice these, so that's up to you. This is, that's exam 1. Today, we're going to move forward into looking at lab 3, okay, algorithms. So the exam on Monday will not cover, some of the things we'll talk about today, but actually, the material that we cover it's cumulative. So the things that you learn for exam 1 will continue to be used for the rest of the course. So any work that we do today will help you with exam 1. All right, so let's see, there are, excuse me, 4 exercises here. These are programming exercises, and let's just look at them. Let's start doing those together and talking about the tools that we need and the analysis that we need to do to solve these problems. Let's go ahead and make a directory. Is there someone in here like to suggest one of those 4 exercises? Perhaps somebody that's already started working on these problems.
2, exercise 2.
2.
Yeah.
I'm going to start by copying one of my existing programs, say exercise 2, exercise 3. I'll rename it to exercise 2. So I'm in lab 3. There it is. Here's exercise 2. Is there any randomness in exercise 2? Nothing, right? Yeah, question.
Lab is due Wednesday, right? Friday.
Is it Wednesday or Friday?
Friday. We decided everything's due by Friday night, midnight.
No, this is October 15. What is that?
Wednesday.
That's Wednesday. It's due on Wednesday. You want it to be due Friday?
Yeah,
Professor,
Every week.
I thought the agreement was every Friday. The lab would be due for everybody. Because you didn't want to separate the dates where one's due on Wednesday, one's due on Friday.
Well, I was thinking just for one lab. What was that, lab 2, perhaps? I can look through these. I mean, if it makes sense. I don't have any trouble.
Could we vote?
I don't have any trouble adjusting the due dates. We just have to cover all the material, so we can't omit stuff. We have to cover everything. And obviously, if we push every due date back to the end of the quarter, you're never going to digest the whole thing. So the deadlines are more like kind of like guidance. This is what you should have done at these points. Otherwise, you're going to have trouble keeping up if you don't have these things done. And I would say that Friday for lab 3 is certainly reasonable. Yeah, that's reasonable. Okay, so I'll move that back, and let me look at the other ones, and I'll look at perhaps changing those all to Friday. You keep reminding me about that if I forget, okay?
Now, isn't it on Friday? Is it on Friday by midnight? Or?
Yeah, Friday midnight. Yeah, so 11:59 p.m. on Friday. What about Saturday?
Well, that's just silly.
Well, the point is, if we push stuff back, you're gonna. I mean, it's gonna hurt you because you won't be able to get everything done. All right, so I'm taking out the random functions. Is there any randomness in the second exercise? No. Okay.
Exercise 4, there's random colors.
Random colors. Exercise 4, you need that rand function. But for exercise 2, we do not. So I'm going to take these. I'm just going to clean this up. I don't think I need those headers. And let's see if we get a build here, okay? Looks good. And we can run that. Says, doesn't say anything. Yeah, that's good. That's what it's supposed to do. Just a new line. All right, let's take a look at the problem statement now. Listing prime numbers.
God bless you.
Now wait a minute, exercise 2, doesn't it require exercise 1, detecting prime numbers?
Not necessarily.
I think they're kind of related, right?
They're related.
Write a console program that reads a positive integer entered by the user. The program computes and displays all the prime numbers between 2 and the number entered. To solve this problem, you need to nest an inner loop within an outer loop. Develop test cases and include them in a multi-line comment. So exercise 2 doesn't make much sense unless we look at exercise 1. Okay, so we're going to do exercise 1.
God bless you.
And I'm just going to move this. Here's exercise 1. Sorry. Detecting prime numbers. Write a console program that asks the user to enter an integer greater than 1. Well, I'm going to just do that now so I don't have to think about it. I'll do it like this. Enter an integer greater than 1. Obviously, we're going to have to store that, so we'll call it n. That's the number that the user enters. So cnn. All right, so I just want to get this detail out of the way so I don't have to get bogged down with little details later on. Right? So let's see if that works. Enter an integer greater than 1. 2. Enter. There we go. So we got that shell of our program running. Let's continue. The program determines if the number entered is prime and writes a message to standard output stream stating whether the number is prime or not. For example, if the user enters 42, the program displays 42 is not prime. If the user enters 47, the program displays 47 is prime. All right, let's create a little more code that acts as a stub for the final. So we're going to add another sort of chunk of logic. It's not going to solve the problem. We're just going to sort of inch our way there to a solution. So just want to get an overview of how the program is going to work right now. So we enter the number, and then let's declare a Boolean value, and I'll call it is prime. And I'll assume, let's say that the number entered in is.
Do you want is prime as one word, or is that?
Huh?
You have bool, and then you have is prime, but you have is prime as one word.
Is prime is true. So is we could do it like this: is n prime. So here we have n, and we're going to declare a Boolean variable. Remember, a Boolean variable is a variable that stores true or false. And so this is a variable that's either true or false. We're going to initialize it to true. So we will assume that n is true. See, the name of the variable conveys its purpose in the program. So it's a record of our sort of assumption about what we're assuming about n. And then we're going to do some logic. We're going to do some research on n. Try to find a divisor for n. So and then if we get a divisor, then do the following: is n prime? We're going to change our mind. We found a divisor for n, so we're going to say that n is not prime by setting our is n prime Boolean variable to false. Yeah.
You have to put the quotation or the / in front of the is and prime.
No, this is not a comment now. See, I'm assuming that we ran the logic, and this is somehow embedded in some logic. And we change our assumption, our initial assumption that n is prime. In other words, this assumption, n is prime, that means we don't have a divisor. No integer between 1 and n, exclusive, divides evenly into n. That's our kind of hypothesis. And then what we're going to do is try each of those numbers between 1 and n. We're going to divide 2 into n. If we get an even divisor, we say, oh, it's not prime. If 2 doesn't divide into n, then we're going to try 3, and then we're going to try 4, and then 5. And if we find one that divides evenly into n, then we're going to change this variable to false, so that we have a record of basically changing our mind, correcting our assumption. We found a divisor for n. There's another way of doing this. I'm going to show you another way of doing it. Right, so I'll comment this out. Maybe this way is more clear. So we found divisor for n. No, we did not find a divisor for n. We didn't find a divisor for n yet. But if we do find one, then we're going to change this, our record, this Boolean variable. We'll set it to false. True, rather. We found a divisor for n. That means that n is prime. Well, maybe that's actually easier to understand. So this is going to be some block of logic here. I don't know what it looks like yet. Right? Some block of logic there. And then now once we've determined, did we find a divisor for n or did we not find a divisor for n? We checked all the numbers between 1 and n. Let me put that note in here. Integers. Try all integers between 1 and n. Exclusive. Because 1 divides into everything, n divides into n, always. All right, so unless n is 0. So here is, so the first step is find a divisor. Now the second step is, okay, let's report the results to the user. So we'll do something like this. So if found divisor for n, if we found a divisor for n, then what are we going to say?
Not prime.
N is not prime. We found a divisor. Else, if we didn't find a divisor for n, I'll just copy that, just make it easy. Then n is prime. If we found a divisor for n, it means that n is not prime. Otherwise, n is prime. Enter an integer, 42. 42 is not prime. Enter an integer, 47. 47 is not prime. We have a stub. It's called a stub. It's a partially completed function. It doesn't do what we want it to do, but it partially works. Okay, so we need to complete this. How do we try all the integers between 1 and n? So what kind of a syntax, a construct that we're going to use to carry out this logic? Huh?
For loop.
For loop. Could be a while loop, but I think a for loop is the easiest, actually. So it's for I, for integer I equals 2, I less than n plus plus I. This is that's a loop right there. Okay. See the stages here? This is where we report the result to the user. This is prompt user for a number. Then we're here. We're going to determine if the number is prime by looking. Determine if the number by looking for a divisor. Determine if the number is not prime by looking for a divisor. Something like this. I'm trying to figure out how to best express it. Trying to find a divisor for n. Maybe I'm writing too many comments here. What do you think? Too many comments? That's not as many comments as I usually write. All right, I think we can weed some of those out. So here in this loop, we actually have to do the division. So if n mod I is 0, what do? It means we found a divisor. That's where we change our mind about our original assumption that we didn't have a divisor. Not original. So we didn't find a divisor. Now we found a divisor. So we set that record. Yes, we found a divisor. In fact, we don't have to continue we've already kind of fulfilled our purpose in the loop. We found a divisor, so we don't need to continue anymore. Although it's not required, it does cut down on some computations by breaking from the loop, and this is called a break statement. So it means exit from the containing loop. If it's a compound loop, that's the inner loop. Exit from the innermost loop. I think that should do it.
Is there a reason why you wrote break after a found divisor for n is true?
Because let's suppose we found a divisor. We don't need to keep looking anymore.
Oh, okay.
We could just keep looking. But that means we're consuming, computer resources. We're running the CPU longer than we need to. So for this little problem, it doesn't matter. We didn't really have to break. But it's more efficient to break here. Enter an integer greater than 1, 42. 42 is not prime. Enter an integer greater than 1, 47. 47 is prime. Looks good. Looks like it works. Let's try some boundary cases. Boundary cases, that means the edge cases, right? Things where the logic might break down for certain certain cases which seem to be different than the others, like 2, for instance. 2 is prime. That seems to work. That's a prime number. Do you believe that? 1, 2, 3. 1, 2, 4, 3, 2, 3, 4, 2. Oops. That's a pretty big number, right? But we don't know. We have no way of verifying that. So at this point, we're operating on faith that we have the algorithm correctly implemented. Yeah. And we're not doing something funny like overflowing a memory allocation. So storing ints is four bytes to an int. Maybe the number is too big for 4 bytes, and that sort of thing. So we're not checking for that. What would happen if I put in a huge number that I know would not fit in 4 bytes? Okay, that will not fit in 4 bytes, and so it doesn't. It's just going to go forever. But apparently, it accepted the number. I think what happened was, oh look at that. Where's that number coming from? It's not the number I typed in. It's not even inside of here. So there's a problem with the program. Somehow this was handled by the input mechanism. You know, the input stream, that input operator accepted this. And it represented it apparently internally as this, maybe. And then we actually tried to find a divisor and couldn't find one. I can't believe that it would run that fast. Is that possible that it could actually run that fast? It says is prime. That means it tried all the divisors all the way up until this value.
So it's gotta be divisible
Huh?
by 5.
What's that?
It ends in 5, the number you entered, so it's gotta be divisible by 5.
It gave you the same answer.
It gives it the same number. But yeah. Oh, this, right. But it doesn't, you know, it tells us the number that we read in is this. So we're pushing beyond the capacity of the system, and we're not checking for this. I mean, we if we're really serious about doing this right, we got to, and we need this. We have to figure out how to, you know, what's the upper limit on, you know, on a number that we can use, and to make sure that the user doesn't enter in a value that's bigger than that. So we're not doing that, and we're not going to do that. This is too much beyond where we are right now in this course. Anyway, that's it. See, for me, what I would do is, you know, like I can see this prompt user for a number. Like I can read this and I say, oh yeah, we're prompting the user for a number. So I wouldn't even put that in there. Determine if the number is not prime by looking for a divisor. Maybe that's good enough. So maybe I'd get rid of that. You know, that's enough of a comment to read. That describes our strategy. Report result to the user. Well, I guess we could leave that comment in there.
When you declare a boolean, why do you declare it false? Why don't you just like if you're declaring like an integer, you just say integer A, integer B, whatever. You don't necessarily have to assign it a value there. But why are you assigning it a value false right off the bat?
Yeah, that's a good question. Let me answer that. And I'm just going to copy. We're going to look at, and this will be the beginning of our next problem. Okay. See, let's. If we can declare it without setting it to anything, but in C++ language, then its value is undefined, is undetermined, is unreliable. In other languages, most other languages, certainly all new languages, will initialize this to probably false, maybe true. Well, certainly they will initialize an integer to 0. But what would you initialize a bool to, true or false? What would your default be if you were designing a language?
False.
False. Because sort of internally, Boolean's usually represented as a 0, like, you know, in C language anyway. So, and 0 is a natural initial state for a variable. integer variable. But the language of C++ and C, this is considered uninitialized, and if you use this variable, you can get unreliable, unpredictable results. Sometimes it'll be false, sometimes it'll be true. So that means and sometimes you don't have to initialize it because later on you're going to set it to something. So that's all right. But we're only setting it to true here. We're not setting it to false anywhere. If we initialize it to true, all right, so if we initialize it to true, then we can't use this, we shouldn't use this name, found a divisor for n. Well, we didn't find one. So we're saying we found one already, but we didn't find one.
So if we were to set it to true, then it would have to be, we'd have to go back to the is?
Exactly. Exactly. And let's do that right now. Let's take a look at that. Let's take a look at that. Say we'll do n is prime. And let's suppose we say false. It works with true. I mean, which one do you want to check, actually? N is prime, we set it to true, we found a divisor. And so we say n is prime is false. This is essentially the same thing. It's just, it's reusing true instead of false, like that. But is it arbitrary? Can we start by saying n is prime? Can we assume that n is prime is false and then determine that, we found evidence that n is prime? Where in this loop can we, how do we, so inside this loop we're going to have to do something to decide that that n is prime needs to be set to true. What do we do to make that decision? What can we test to change our minds about? It's not exactly changing our mind, but to declare that, our original assumption that n is prime, we declared it as false, but we found evidence that, it is in fact prime. So, you see the problem?
No.
Yeah, I mean, you see the problem with this? You actually need to think about this. So if we find a divisor, we know, if we find one instance of a divisor, we know that n is not prime. So all we have to do is find one divisor. But how do you declare that n is prime? Well, I checked every single divisor, and I didn't find any. But I checked every potential value between 1 and n, and I didn't find a divisor. Then I can declare that n is prime. So you basically can't go in this direction. You can't make the assumption here that n is prime and then declare that it's true. You would have to do something like, go into this loop. Then you would need to have a Boolean variable like that. Did we find a divisor? So we could do it like this. I'll show you how that would work. It's hard to explain this. We would in fact need this found a divisor. And we didn't find a divisor. Now we say, we found a divisor. And then if we found divisor for n, then we can reverse our assumption at that point. That's a lot of extra code, and we just don't need that. We're introducing a new variable, and that's really not needed. Well, maybe this is easier to comprehend. What do you think? Oh, that should be false.
Alright, quick question.
Yeah, wait a minute, that should be false.
For when you're in the for loop and you're doing n mod I, why do we have two equal signs there?
Because we want the comparison operator. What happens here is this n mod I, that expression evaluates first. Okay? And then the result, n mod I is an integer. So I divides n if the remainder after dividing n by I is 0. So remember, n mod I gives the remainder. We take n, we divide by I, like 3 divided by 2, and we get the remainder 1. Does 2 divide into 3? No, because it has a remainder of 1. How about 4? 4 divided by 2. What's the remainder? 0. So if you get a 0 remainder, it means you found a divisor. 2 is a divisor of 4 because 4 mod 2 is 0. Is that all right? You got to think about it on your own. Right? I don't think if someone was lecturing to me and they were saying that, oh yeah, I would probably get it because I know this stuff. But it's the kind of thing where you got to think about it on your own, right?
I'm a little confused about using the Boolean true false in like the for statement. So
Yeah.
basically, if you have like if, and then you have a variable in there that's related to the Boolean, and you set it to true.
Yeah.
So is it checking that variable to see that it matches? Like,
Are you talking about this line here?
I'm talking about where you change. It was in your original, but I'm looking at what
Down here.
It was where you had the if.
Here, right here?
No, not it was. You have like originally you had written if and in parentheses found divisor for n.
Yeah, the bottom, more down.
Oh, right there.
Oh, there you go. Yeah. So is that checking to see if that matches the last time that variable was?
No. If, let me tell you about if.
Okay.
If statement looks like this, it's got the word if, then it has an open parenthesis right here. Then it has an expression that evaluates a true or false. And then it has a closing parenthesis. And then it has optionally a brace because that allows multiple statements. So if the expression that evaluates to true, then we execute the statements that are child statements of the if statement. If the expression evaluates to false, we do not execute the child statements, but we go on to the next statement in the program,
Okay.
which would be down there. So that's how it's, when you look at this, don't like, when you look at this expression I have highlighted, it has nothing to do with n is prime. And it doesn't matter if this executed or didn't execute. We initialize it here. This may have run or may have not run. If this runs, it changes the value found divisor for n. If this doesn't run, then the initial value for found divisor for n is used. So it's whatever, remember, it's a variable. So at this point in the code, we don't know if it's set to true or set to false. It depends what the user types in. That's why we call it a variable. It's a storage location in memory. And it contains, in the memory, you've got these bits. And they have some magnetic property. They store information. This bit is either a 0 or a 1. And we don't know when the program runs if that bit is going to be set to a 0 or set to a 1. It depends on how the program executes, which depends on what the user types in at the keyboard. So we call these things variables. There's another question back there.
Yeah, I was going to say, so if you put equals true after it, it's like the same thing?
Yeah. Exactly. This is the same thing because this is another Boolean expression. So remember, the thing in between the parentheses is some expression that evaluates to true or false. So the simplest expression is just use a Boolean variable directly. That's true or false. It's good enough. Well, we can use a Boolean variable and compare it to this keyword in the language, which represents a true, it's a constant value, true Boolean value. So we can do it like this, but this is extra verbiage. We don't need this. Yeah.
It just seems like it makes it like easier to understand. Like if you're just literally reading it, you're like, okay, if the divisor, if we
Absolutely.
true,
Absolutely. There are many programmers that will write it exactly like this. They say, this is readable, this is how I'm coding it up. And then you're going to find another group of programmers that says, that's good enough for me, and it's less to type and less to read. So you'll get, you split into two groups at this point. I would say that for the people in this class, my experience is this expression is easier to comprehend. But if you become a programmer, and later on, you're going to be reading other people's code that uses that. So you got to get used to that anyway. So you have to be very kind of nimble, flexible, and you'll see different programming styles, and you've got to be able to sort of handle all those variations. Well, when you're coding up a solution for yourself, you're in a team, and your team says, this is how we're going to do it because it's going to reduce the number of logic errors that we introduce in code, and we're all going to be able to read each other's code more easily. Let's all agree to write it like this, and then that's what happens. So then you develop what's called a coding guidelines or style guidelines, and it helps the team to work together. It helps you also in reading your old code as well if you stick to certain conventions. All right, so let me move on and look at exercise 2, listing prime numbers. Now the reason I put this exercise in here is so that you have some experience. Well, there's multiple reasons, but the main reason, the initial reason, is that you can practice writing nested loops. A loop within a loop. Write a console program that reads a positive integer entered by the user. We did that already. The program computes and displays all the prime numbers between 2 and the number entered. All right, I'm going to move this back a little bit. This is too hard to look at. I'm just going to kill it all. So enter an integer greater than 1. That's good enough. Now we're going to, print all the prime numbers between 1 and n, the number entered by the user. Let's print all the prime numbers between 1 and n. So that means we've got to, if 2 is prime, let's print 2. If 3 is prime, we're going to print 3. If 4 is prime, we're going to print 4. Well, it's not prime, so we won't print 4. So we'll print 2, 3, 5, 7, right? We're going to keep going up like that, but we don't know how far to go.
Considering that the description of this exercise says it's going to print out anything between 2 and the number itself.
Yeah.
Shouldn't we write greater than 2 then, rather than greater than 1?
Oh, we could do that. oh my gosh, greater than or equal to 2 and less than or equal to n. That's more precise, right? Because the user enters a 7, we're going to print 2, 3, 5, 7. If the user enters an 8, we're going to print exactly the same thing as if when we printed when the user entered 7. So, I mean, what do you do next?
I have a question.
Yeah.
From the beginning, like you put int n and then semicolon. Can you do int n equals 0?
Yeah,
Okay.
no problem. Int n equals -1. You can do that. So int is any integer value, which could be negatives or 0. But there's a limit internally, like we saw that earlier, right? Can't be really big because it's 4 bytes. It's the max. So something like 2 billion, I don't know what it is. 2 billion, I think. 4 billion. So isn't this the hard part here? Like, what do you do now? We prompted the user, we read the number in, it's stored in a variable n. And we looked at an exercise already that showed us some code how to decide whether a given value is prime or not. So we kind of need to use that. We're going to check 2. Let's use that. We have some looping code. Let's call it some logic. We used our prime checking logic. So we're going to look at 2, use our prime checking logic to decide whether to print 2 or not. Then we're going to try 3, use our prime checking logic to decide whether 3 is prime, and we print it or not. And we're going to try 4, and then we use our prime checking logic to see whether 4 is prime or not, if it's prime, and so on. So we need to sort of reuse. We have some memory of having looked at and developed prime checking logic. We're going to need to use that repeatedly. And the other problem, we just ran it once. You know, the user entered in 42. We ran our prime checking logic, and we were done. But now it's different. Now the user enters 42. And we need to consider every number, 2, 3, 4, 5, all the way up to 42, and rerun our prime checking logic for each of those values. Now the prime checking logic is a loop. And then the values 2 through n, well, we need a loop for that, right? I don't see how else you can do that, because n is not determined in advance. So we need to have a loop within a loop. It's called a nested loop. This is kind of like the point where you have to think creatively. So let's do this. I'm going to declare a variable k. We'll set it to 2. And k is less than or equal to n. We'll do plus plus k. And then we have, you know, if, let's do it like this. Bool k divides n. We'll say that k divides n is false. I know I'm not going to set it true. I know that that won't work. I know in advance. So maybe you can't see that at this point. So if you're going to guess true or false, you might start saying true. But I already know, because I've done this problem hundreds of times, that I'm going to set it to false. So we have this Boolean value, k divides n. And then we're going to, you know, look for a divisor. And if found, set k divides n to false. True. But I'm going to leave this part out for now. And then after we decide, do does k divide n or not? Oh, wait a minute. This is not right. Sorry, this is not right at all. This is not right at all. So we found a divisor for k. We didn't find a divisor for k. Sorry. If we did not find a divisor for k, if found a divisor for k is false, then we're going to print k. We'll put a space there so that next time we print the next k, it'll have separation. So I want to know, we're looking at k equals 2 through n. And I want to know if k is prime, then I'll print it. If it's not prime, I won't print it. That's what we need to do. So if we find a divisor for k, that's false. Yeah, if we don't find a divisor for k, then it's prime and we print it. Seven. 2, 3, 4, 5, 6, 7. We're printing every number. So the code assumes that that we did not find a divisor for k. But let's add the code. Do you see where we're at here? Maybe I'm just going to do it. For integer I equals 2. If k mod I equals 0, we found a divisor. I shall put it on the next line here. That comment looks better there. Actually, we just get rid of that comment. It's too hard to read it. So we start by, we have a k. We're going to check, k is going to be 2, 3, 4, all the way up to n. We want to decide, we want to see if we can find a divisor for k. If we do, we're not going to print k. So first we're going to say that we didn't find a divisor, so we set that variable to false. And then we check all the values I between 2 and what?
Okay.
Well, k minus, we don't want to hit k itself because k will always divide into k. So you got to make sure that I is strictly less than k. Oh, sorry. Good catching that. So we certainly don't want to use n there. You know, n is just the upper limit. We're trying to decide whether k is prime or not. So we've got to stop when we get to k minus 1. And so we're going to try every value I from 2 to k minus 1. And we'll do k mod I. If it turns out to be 0, we found a divisor. We set our Boolean variable found divisor for k to true. And then we break the loop. You know, if we leave this break out, it's still going to run correctly. It just won't run as fast. And when this break, oh look, there's a for loop here and a for loop there. What does break do?
You reach the loop you're inside.
Yeah, it breaks the inner loop. So it breaks this loop. So we're still inside the outer loop. So we break this outer loop, and then we're going to say, well, you know, the loop ran, and I don't know if we found a divisor for k or not. That's why we need to keep track of that. So this is our tracking variable, our state variable, whether we found something or not. If we didn't find anything, if we did not find a divisor, it means k is prime, and so we're going to print it. Otherwise, we print nothing. You see what I'm doing? Look at my spacing. See, I have one line space there, a line space there, a line space there. See, I'm being very careful about making the code sort of neat. And see the way I have indentation? This for loop here, this is you see that brace up there and this brace down there? This is all a single statement, a compound statement. It's got a lot going on the inside. The child statements are complicated. This is a single statement. And that opening brace, which is here, and this is a style to put it on the next line, but I'm putting it here. And the closing brace is underneath that F. And this makes the code more readable. So you need to do this in this class. Your code has to be indented in a logical manner. You can use a different style if you like, but the style, you have to adhere to it consistently, and it has to be, of course, make sense. So this for loop, inside the for loop, how many direct children, how many direct child statements exist inside this for loop that I have highlighted? How many direct child statements? How many? Yeah, no, I don't want grandchildren. How many children does this for statement have? 3, very good. I'm going to show those to you. This is the first child. This is the first child statement in that for loop. This is the second child statement in the for loop. That's the second statement. This is the third statement directly in that for loop. This statement, the third statement in the for loop, itself has a child statement within it. The first statement in the for loop has no children. It's just a simple statement. It's not a compound statement. It's a simple statement. The second statement is a compound statement. It has child statements within it. Oh, actually, it only has one child statement. It has that. It has one child statement. But this conditional statement, this if statement, has 2 child statements. This is the first statement, and this is the second statement. And the indentation that I'm showing here expresses the relationship between these statements. If a statement is a child of a parent statement, we indent the child statement relative to the parent. Is everybody clear about this? This is very important, by the way. This is how people read code. Okay. Let's check, our logic here. Let's see if this works. Seven. Oh, wait a minute. What's it going to print? 2, 3, 5, and 7.
That's what he had.
Well, he updated. He doesn't have ...
2, 3, 5, and 7. All right. What's it going to print? Same thing. These are all the prime numbers between 2 and 47. Are there any bad numbers in there? Are we missing anything? Anyway, that's it. That's how you do problem 2. And later, so the thing here, you know, the indentation, the creative process that you go through to solve the problem, using the use of Boolean variables, talked about that. And nested loops, we talked about that. And in a future lab, we're going to revisit this problem. And there, you're going to simplify the code by using a function. So you won't have a nested loop anymore. You'll take the inner loop here. Actually, you'll take this whole chunk of code right there, and you'll push that into a function. And so this loop here, the outer loop here, will just have a simple call to a function. So you'll see a kind of a simplification. That's coming up, maybe it's in the next lab, I think, or maybe the lab after that, I'm not sure. So it's 1 o'clock, that's enough, right? We're good? Good? You're all worn out, right?